Electrical energy is transmitted at high voltage to a remote farm using an overhead power cable. Each of the two wires in the cable has a resistance of 2.5 ohms. The step-down transformer in the farm has a voltage ratio of 5. The transformer is ideal and 100% efficient. It supplies a power of 40 kilowatts to a resistive load at the farm at a voltage of 250 volts. What's the rate at which electrical energy is transferred to thermal energy in the overhead cable? So drawing this, we have the two wires in the cable. Let's draw the coil, and then the other wire that makes that cable. And these have a resistance of 2.5 ohms. Now, a lot of people might think they mean two wires joined together, which I think is actually a reasonable interpretation. But a lot of the times when they mean two wires in a cable, it just means one wire to connect to the top end of this coil and another wire to connect to the bottom end. And then this will be at some potential be primary. Then this will be supplying the load here, which is at 250 volts. Because it's a voltage ratio of 5, we can just multiply 250 by 5 to get 250 volts in the primary circuit. So how do we get the energy lost as thermal energy in these two wires? Well, the first thing to notice here is that the voltage dropped across the wires would not be the same as that voltage dropped across the coil. That is the good kind of voltage that we want dropping, as the power from this section will be transferred into the secondary circuit. So if we can work out a current in the primary circuit, we can multiply this to get I squared R, and then multiply this by 2 to get the power. Because we can work out the current, and then if we use current times resistance, we could get V, but it's easier to just sidestep this and just use I squared R, because we know the current and we know resistance. So there's no point really working out whatever voltage is dropped, as we can just use that equation, I squared R. So we can get the current IP as the power it's supplying, given that it's 100% efficient transformer process. This doesn't mean it's 100% efficient in the transmission on the left-hand side, just that converting the power from the primary to secondary is 100% efficient. So 40,000 over 250 is that primary current. And then if we square this, multiply by 2.5, and there's two of them, we should get the power lost. So this is equal to IP squared times 5. Now we just need to find out what IP actually is. So we could cancel out a factor of 10 here. 125 goes into 1,000 8 times. So this would be 8 times 4, because 1,000 over 125 is 8, and then 8 times 4, this gives 32. So this is 32 squared times 5. Now, how to do this calculation, you can do in a number of ways. So I could just do 32 times 32, which is 900, plus 2 times 30 plus 2 times 30, which is 120, and then plus 2 squared is 4. So just kind of doing a grid in my head, and then times this by 5, we get 1,024 multiplied by 5 equals 5,120 watts. So the answer is C, 5.12 kilowatts. It might have been easier as well for the calculation. Again, saving time is really important in the NSAA, so if you can find easier ways to do the arithmetic, it might have been easier to do 32 times 32 times 5. So 32 times 5 is 160. So we'd have 32 times 16 times 10. And if you know 32 times 16, if you know your square numbers, 16 times 16 is 256. And then 256 times another factor of 2 would be 512, times another factor of 10, we get 5120. So just to break that down, we get 2 times 16 squared, 256, times 10 gives us 5.12 kilowatts. Again, hopefully that makes sense. The question is a bit ambiguous about the wires. So if you did get a factor of maybe 1.28, an answer of 1.28 by splitting the current into two, I can see where you might think that. I also might have thought the same while doing the problem. But usually here they just mean the two wires, one connecting the top, one connecting the bottom, in order to carry the current back and forth. Again, with these transformer questions, you should always use I squared R for power lost, because you can always get the power in the cable. And if you know its resistance, you can always get the current in the cable. If you know its resistance, you can use I squared R. Whereas we don't typically know the voltage dropped across the wire, just a voltage dropped kind of across the coil. Hopefully that makes sense. But again, any questions, let me know in the comments.